This is the SIR model. So this is a way of projecting or modeling the spread of some disease through a population. So the fundamental idea here is that every person in our society is in one of three different states. Either they are currently infected with the disease, they are susceptible to the disease, or they're recovered or maybe removed from this situation. And the general idea is that people who are susceptible may become infected, and people who are infected are going to, at some rate, recover. And this R stands for recovered, or sometimes people call it removed, as in you either get over the illness, or you don't. Either way, you are removed from our model. We're just going to call this recovered, though. So to set up a differential equation, we need to talk about the rate of change now of each of these three groups. And all of the change that's happening is people going from one group to the next group. So we need to come up with some idea for what this rate of change looks like. How quickly are people going from infected to recovered? And for this SIR model, we're going to say that this looks proportional to the number of people who are currently infected. If 100 people are infected, then our rate of recovery is maybe 1 person a day. But if 1,000 people are infected, then maybe it's 10 people a day. The idea is that if there are more people in this infected group, then the total number of people who are recovering is greater. So we're saying this is proportional to I. And when we say it's proportional to I, we're saying that this rate of change, this going from infected group to the recovered group, is going to be equal to some constant times I. And we're just going to call that constant B for now. Okay, this type of setup, being proportional maybe to Kp, we've used it before, is setting this up to be an exponential. However, the total number of people who are infected is going to be changing. So we're not actually, so it's related to being an exponential, but the solution is actually not going to look like an exponential. That said, it has this same property of being proportional to one of the populations. This other part, this rate of change of people going from susceptible to infected, we're also going to say is proportional to something. But for this one, we have to take into account both the population who are infected and how many people who are out there. So if, for example, we're starting off, let's say that 1% of people are infected, this is at some time t equals 0, no one has recovered from it yet because it's still early on, and 99% of the people haven't yet encountered this. So the idea is that when this percentage is so big, the rate of increase, or the rate of spread of this virus, of whatever this disease is, should be proportional to how many people are currently infected. So this is going to look like, so proportional to infected. However, when the total population that could possibly be infected is dropping, then the rate of change from the number of people moving from susceptible to infected is also going to drop. So if this population, if this susceptible group is smaller, then fewer people are going to be moving over because there are fewer people who could possibly get infected. So this is proportional to IP. So put another way, it is some constant times IP. And this is the same thing as the logistic curve that we've been talking about. P, oh, I said P. We're talking IS, susceptible. So this should be A times IS. So this susceptible number is the percentage of the population that still hasn't been infected. So this thing is the setup that gives yield to a logistic curve. Okay, now that we've set this up, this is all the assumptions that we have to make in order to get some sort of model of how these different numbers change over time. That said, it's not quite in our mathematical format yet. What we want to know is, what is the rate of change of the number of people in this first group? The rate of change of S. Well, ds dt, well, how does this change? How does this number, the number of people in this first group, change? Well, it changes when people leave this group for the second group. So whenever that happens, that's going to decrease the number of people who are susceptible. When somebody gets sick, then they're no longer susceptible. The total number of people who could get sick decreases. So ds dt should be negative. Our total population of people who are susceptible is going down. And it's going down at a very specific rate, at a rate AIS. So ds dt should be A times I times S. Okay, we're gonna skip, or let's go ahead and do this one. So di dt, how does the total number of people who are currently sick change over time? Well, people are coming into this group from the susceptible group when they get sick. And unlike with the susceptible case, our second infected group is going to be increasing at that rate. So people are moving from one group to the other, so they're leaving susceptible at a certain rate, and they are entering the infected group at that same rate. Okay, cool. So that's how quickly people are moving into this group. However, people are also leaving this group. People are going from being infected to recovering at a certain rate. So this is the BI rate. This is the number of people, this is the rate of people recovering. And because recovering involves leaving the I group, this term is going to be negative. All right, and then lastly, dr dt is the rate of change of the recovered group. Well, the only way this number changes is when people enter this group from the infected group. So this is going to be equal to B times I. Okay, and so now we have this in a more mathematical way, or in a mathematical format. And what we have is a system of differential equations, which we can solve. It just takes a fair amount more work. Differential equations is a really big field. Since we're only doing this in the last week of class, we're really just getting a taste of this. So rather than solving this algebraically by doing some sort of technique, we're just going to ask a computer to do it numerically. So one of the main reasons we talked about Euler's method, where we have some sort of slope field and we're taking individual steps, is that that's how a computer solves a system like this. It starts off with its initial conditions, it figures out the current rate of change, and then it keeps moving along step by step. So rather than trying to solve this directly, we're going to ask a computer to do that for us.